This is the sixth video of the summary on Battery Day. It is the first part on the cathode and covers the materials and the process optimization.
Let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. What sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are.
You need a stable structure to contain the ions. Basically, that holds its shape as you're moving these ions back and forth.
The thing to consider is just fundamentally what the metals are capable of, and that's what we have on the chart here. Dollar per kilowatt hour cathode of just the metal versus the energy density of just the cathode. You can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours. But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. That's what we've been working on with our high nickel cathode development, which has zero cobalt in it. We can get a 15% reduction in cathode dollar per kilowatt hour.
In order to scale, we really need to make sure that we're not constrained by total nickel availability. If you look at watt-hours per kilogram at the cathode level of iron, it looks like nickel's twice as good. But when you fully considered at the pack level, everything else taken into account, nickel is about 50 or 60% better than iron. Iron is not as good as nickel. Nickel is like 50 to 60% better, but it's actually pretty good. Good for stationary storage and for medium-range applications. It's relatively straightforward to do a cathode that's 2/3 nickel, 1/3 manganese, which would then allow us to make 50% more cell volume with the same amount of nickel.
And with very little energy trade-off.
I think we need to have a three-tiered approach to batteries, starting with iron, that's kind of like a medium range, and then nickel manganese as medium plus, intermediate, and then a high nickel for long-range applications like Cybertruck and the semi. Because something like a semi-truck, it's extremely important to have high energy density in order to get long range.
Beyond the metals, actually the cathode process itself is a big target. 35% of the cathode dollar per kilowatt hour is just in transferring it into its final form. Here's a view of the traditional cathode process. If you start at the left and you have the metal from the mine, the first thing that happens is the metal from the mine is changed into an intermediate thing called a metal sulfate, because that happened to be what chemists wanted a long time ago. And then when you're making the cathode, you have to take this intermediate thing called metal sulfate, add chemicals, add a whole bunch of water, a whole bunch of stuff happens in the middle, and at the end, you get that little bit of cathode and a whole bunch of wastewater and byproduct. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and zero wastewater. Much more scalable solution. We can also use that same process we showed on the previous page to directly consume the metal powder coming out of recycled electric vehicle and grid storage batteries. So this process enables both simpler mining and simpler recycling. And eventually, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants and vehicles to electric. At that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why. The difference in the value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. And we recycle 100% of our vehicle batteries today.
To date, it's been done by third parties, but we think we can recycle the batteries more effectively, especially since we're making the same battery as the thing we're recycling, whereas third-party recyclers have to consider batteries of all kinds.
The recycling resource is always 10 or greater years delayed because batteries last a really long time.
Long-term, new batteries will come from old batteries once the fleet reaches steady state.
If you want more on the Tesla Battery Day, you can continue with the next video, or you can go to the first video that provides an overview of all the videos.